For the first lab, we were to measure an object moving at a constant velocity. I chose to measure a peanut butter can rolling across a flat countertop. We had to track the motion of the object to observe Newton's second law. I uploaded my video to Tracker in order to get the position of the peanut butter can. As you can see in this first image, the peanut butter can is on the countertop. The small blue line is the calibration stick that was used to put the peanut butter to scale. It is 7 centimeters in diameter, and I changed it to be in kilograms. The next picture shows the axis that was used. The origin is put at the center of the peanut butter jar. I switched the axis so that the positive x direction is going to the left. This way, the peanut butter jar is moving in the positive x direction. I picked frames 42 through 92 to use for the video. This is because the first few frames, the can was accelerating and not moving at a constant velocity. As the can rolled across the countertop, I tracked the position of it using the circles on the screen. The circles were used at the center of the peanut butter can. As you can see, it makes a straight line, proving that it is moving in a constant positive velocity. The dots represent the center of the mass of the peanut butter can. The table on the right shows the position versus time of the peanut butter can. It is a straight line, which means the constant velocity. On a position versus time graph, the slope is equal to the velocity, which proves that it is constant. In order to calculate the velocity, the initial velocity was first used. The positions that were used are the second position, due to the fact that the first was not equal to 0, and the third position. The initial velocity is found from subtracting the positions of those points and dividing it by the difference in time. This is slightly different from the average velocity, which is 0.321 meters per second, because at the beginning the can may have still been accelerating and the positions may have started too early. I edited a Python file to represent the model that was shown through Tracker. This first window shows where I edited the ball's mass, which was found online, and inserted the ball's initial position and initial velocity. I also changed delta t to 0.01 so that it could be measured accurately. This next screen shows where I changed the ball's velocity and positions equations so that they would equal Newton's second law. The velocity was changed to the initial velocity plus the net force divided by the mass times delta t. The position was changed to the initial position plus the ball's velocity times delta t. This was all while t is less than 1.668 seconds, which was the time that the can was filmed. When I ran the code on Python, this is what happened. The top image shows the ball moving away from the origin, and the graph shows the ball also moving away from the origin in a constant positive direction. This is consistent with the Tracker version of what we recorded. If I had not changed the direction of the origin at the beginning, it would be moving in the negative direction. We then compared the predicted motion versus the observed motion. The graph here shows that the red line is the predicted motion based on the Python script. The observed motion, which is represented by the blue dots, is slightly off from the predicted motion. This could be because the peanut butter can rolled in a slightly diagonal direction towards the back of the counter, or that it was still accelerating and not at a constant motion when the positions were being tracked at the very beginning. It could also be a result of me not clicking in the direct center of the peanut butter jar when recording the motion. In this experiment, the forces on the bottle included friction, gravity, the desk pushing on the bottle, and the bottle pushing on the desk, as well as the initial push. This all evened out to be a force net of 0, which created a constant velocity. This proves Newton's second law, and it also proved Newton's first law since the net force was 0. It also proves the momentum principle, which was 0 in this case.